Ok, parce que ça marche. Est-ce que c'est bien ici, le voir ou non?
Oui, je vais tourner la caméra, je vais tourner l'autre caméra. Non, je vais mettre celle-là sur toi et l'autre sur le modèle.
Ok.
Ok, c'est bon. Ok. Merci. Je vais. Okay, I will force it. Sorry. No problem.
Bon. Bonjour tout le monde. Good afternoon. Sorry for the delay. I will start my presentation about our millimeter wave lab. I will speak about circuits, modules, and interferometric systems. First, we all know that microwave starts more or less around 300 megahertz, and we wish to reach 300 gigahertz in our applications. It means the wavelength is between 1 meter and 1 millimeter. And generally, we speak about millimeter wave range from 10 millimeters to 1 millimeter. You can see here in red. Currently, our works cover K-band, V-band, W-band, more or less up to 110 gigahertz, and we'll start to work in D and V bands hopefully after we have more K-band. Speaking about 5G and whatever, 6G, 7G, whatever, people want to have like more speed, use millimeter waves for communications, but you see from the at least 20 or 30 years, integrated circuits are not really ready at a very low cost. That's why even today, 5 years after, we still stay under 6G, 6 gigahertz, and to have some application 24 gigahertz, but we're not reached yet, depend or in the future, in few years. For our research applications, we work in interferometric transceiver for high data rate communications. You will see why interferometric transceivers. That ones are a bit different for conventional transceiver, and I will explain. After another area of research are radar sensor covering from 24 gigahertz to around 100 gigahertz. We start to work in joint radar communication system 2 years ago, and also in the broadband quadrature interferometric mixer covering dozens of gigahertz at once. For the research activities, I will present some circuits and model design using commercial software after prototype fabrication and characterization using vector network analyzers, probe station, and dedicated test benches. I will start with circuit characterization. I put there MHMIC, but can be another technologies. Especially, we need to characterize the circuits in order to create computer models to have very accurate simulation, system simulation before prototype fabrication and test in the lab. Because all those applications are extremely expensive. You think about thousands of dollars for each single circuit, and we don't want to waste our money. First, you can see here a photo. You can see here a photo of one of millimeter wave probe stations. We start building this one in 2007.
Please, Habib, check. No, just approve the person who tried to connect, please. Sorry.
No, it's okay. We start building this millimeter wave probe station with the help of our long-time partner Focus Microwave, using Cascade probe station 900 from Professor Dedindi, and we built this one custom made, if you want. Was one of the first in the world operating up to almost 100 gigahertz. You can see in this one the vector network analyzer here. Position millimeter wave positioner that can accurately move the probes with few microns in X and Y plane and less than 0.1 microns on the vertical. Also, we have a digital oscilloscope, digital microscope with the camera. And you can see in this corner a typical MHMIC circuit when we try to put calibration kits and as many as we can circuits in order to reduce the cost of application cartridge circuit. We'll characterize the circuit and we'll generate computer models for initial simulation. Concerning fabrication, we fabricate using MHMIC technology in 5 mills. Why? Because at this very high frequencies, the transmission lines are extremely short. We speak about some hundreds of microns, around between 400 and 700 microns, and the width of the line for this permittivity it's exactly the width of the line of the 50 ohm. That's why we will work in 50 ohm, but not only we reach the maximum capabilities in fabrication. We try to work even with the Cartesian impedance very close to 100 ohms. When the line is so thin that it's almost the limit on the fabrication, around you see 3 microns worth. On these circuits, we need to characterize all the circuits with 2 probes. That's why we fabricate several ones. Just to see the thickness is like 137 microns. The transmission lines are 1 micron gold metallization on the ceramics, and the resistors are integrating with the diamond oxide, 100 ohm by square. I show here another circuit, and you can see that first, we cannot connect any loads from external. It means always when we need to measure 2 points, all the others are connected by internal loads, and the loads, I will present how we will do it. And once again, if we work in the Cartesian impedance of 70 ohm, we have acceptable ratio between the length of the λ/4 transmission line and the width of the line. If the circuit is not symmetric, you can see that for a 3-port circuit, we need 3 different circuits, for a 4-port 6, for a 5-port 10, and for a 6-port 15. This is generally too much and too expensive, and we try to put, if possible, all the circuits we need in one single time. And it's preferable to fabricate 2 because we never know what's happening. And that's why we'll look to the symmetry, the maximum symmetry of the circuits. If you see, for example, the simple circuit like the power divider here in the bottom, it's perfectly symmetric over the y-axis, here x-axis, and we don't need to measure 2 times between the port 1 and port 2, because the port 3 is perfectly symmetric to the port 1. It means for the 3-port, we can reduce to 2 circuits. For the 4-port, we can reduce to 3 different circuits. You see here, 3 circuits for a hybrid coupler. And for a 6-port, we can have all the measurements measuring 7 circuits. Of course, all must be perfectly, fabricated, and also positional errors must to be avoided. We speak here of errors of 1 or 2 maximum microns in alignment in X and Y, and on the Z, less than 0.1 micron. If not, the circuit is damaged in the very first landing of the probe. And we need to be really careful to measure a circuit, because a circuit like this was like maybe more than 1,000. And you don't need to watch the circuit. We start with very simple circuits. It's one of the circuits in photo here. And I start with big band, 60 gigahertz, where the ratio in between the λ/4 length and the width of the substation is very, very close. It means the performance will be good, but the bandwidth no larger than maybe 5 gigahertz. Here is a detail of the load. Each load is integrated and the ratio is like 1/2 because we need 50 ohm from 100 ohm by square. Instead of having short circuit that is not repeatable, it's very dangerous for such a thin substrate. We work with like a kind of lambda/4 transmission line, and if this one is in open circuit, very close to the end of the resistor, we give a short circuit. And for example, here we see a measurement between the port 1 and the port 3. The other ports are terminated by the loads. Once again, we cannot connect external loads like usual in measurements in microwave. And you can see even the marks of the landing. And usually we cannot land more than 1 or 2 times because the circuit will be damaged. That means no error in position. Concerning the performances, it's one of our oldest circuits. Usually, if we have here 20 dB, the energy, the power is 1/100. -30, 1/1000. This is not for the millimeter wave guys, but for beginners. Okay, and usually if we keep all that parameters less than -10, -15, we can work with the circuit. We try to cover here no more than 2-3 gigahertz to reach several, maybe 1 gigabit per second. So the circuit is good enough for this purpose. And concerning the power splitting, must be equal. It means 3 dB. It's very close to 3 dB. And in the end of the band, we have around 1 dB. For the phase difference must be 90 degrees. And it is. You can see in green that we have maximum 2 degrees of error. Once again, this includes the positioning of the probe, where each maybe 10 microns, it's 1 degree. That's why all those measurements include also the measurement error. The circuit usually it's bad. For a power divider, you can see a power divider that was first developed in our laboratory. It's a kind of combination between the red trace and the conventional Wilkinson. The problem always with millimeter wave power splitter before this one, it was designed by one of my former students, now my collaborator, Charlie Hamoum, is that the connection of this resistor must be extremely short, and it's not possible usually. And that's why in a red trace coupler, we have something like transmission lines longer. Here, if we add the transmission line of lambda/2 to connect, we can have like an open eye. That is the beauty of our circuit, an open ring. And power is split into different parts. And the resistor is still there. And that resistor will allow the isolation between the port 2 and 3 to be very good. Of course, the circuit is perfectly symmetric on the y-axis. That's why we need only 2 meters. If you look to the performances, we have a very, very good match around -30 dB over the band, up to 62 where we work. And quite good isolation between the ports 2 and 3. Once again, if it's a pitch junction, this isolation is -6. For a circuit having several ports, in this case the 6 port, you can really see the symmetry of the circuit along the y-axis, and all the other ports are symmetrically. The port 7, we don't use it, it's connected to the load, and the port 5 and 6 are here. And you will see how this circuit is integrated in the interferometer with other MHMIC circuits, other components, and integrated circuits to build the receiver. Using that measurements, our first step, we build several circuits. And our approach is to export all the data in ADS and after to simulate and to see if we really can use it for high data rate transmission with an acceptable error vector modulation. And that's why we export from the vector network analyzer all the digital DAC, digital access component, and we perform simulation. The first step is to double check if we export correctly all this one, because it's not really easy, because the name is only sport 1, 2. And we keep the name of the file to have the correct name of the port. And we double check if the photo or whatever image JPEG or simulation on the screen of the vector analyzer is exactly the same shape and the same like in our simulation. Like this, we are like really sure that all the data access components are correctly imported in the software. Once again, we can see matching all the ports. I will be short here. Transmission in between the ports and the output at during -60 dB, because we pass with by 2 couplers, and we have an additional loss because of various application errors and positioning, coupling. Those phase shifter must be 90 degrees, and honestly, it's very difficult to evaluate all these ones in all the frequencies to see how it's working. And that's why Dr. Engel introduced it in the 70s for the very first 6-port or 5-port circuits that were used in the vector analyzer, building vector analyzer. A very interesting equation, and introduced the QE points, we call it. In this time, it was 3 QE points, but we used the same idea to plot only 4 points, and that points will contain all the values over the frequency, amplitude, and phase. And it's very easy to see how that 3 points go around on the IQ plane. And in ideal case, the 3 points are on the unity circle and spaced by 90 degrees. We can use 2 definitions, 6 over all the outputs, the port 5 doesn't equal over all the outputs. And you see, I keep all the colors that we have in the lab. On the oscilloscope, each company like Keysight or Tektronix have different colors for each input. And I was, to compare simulation and measurement, I always keep the same colors to be easy to recognize the signals in the time domain when we measure a system. For example, here the errors are not so big. We are quite close to the unity circle. And also this phase rotation is normal because we change the frequency, but always the phase error is less than 1 or 2 degrees. In the same, if we divide like 5/6, we have the same points, but the rotation is clockwise rotation. You can see always it's 1, 2, 3, 4. If this is not correct, we'll try to see where is the error. It's in the name of the file, or it's sure not in the design, because if not, the circuit doesn't work correct as an interferometer. First, to characterize the circuit, another method is to use the measurement and to put an ideal detector. And we'll double check what's happening with the magnitudes over the phase variation, where we know that we need to have the correct order 1, 2, 3, 4, and also the phase difference of 90 degrees, and if possible, equal magnitude. If we put an ideal power detector, all the shapes are sinus or cosinus, and also, but the only difference is the minimum is not so sharp. Another definition that we generally use in order to demodulate at once whatever signal is transmitting without knowing what kind of signal is transmitting means whatever QAM PS key. We introduce a kind of vector, we call it gamma, and you see in the page of equation. that use the difference in between voltages, the output of the interferometer, to display at once on the oscilloscope or on the complex plane a point. At that point, usually it's a symbol, and the symbol is carrying several bits. And usually we go work with between 2 and 64 symbols because of the, you will see, because of the noise that we have in milliwatt. After we'll introduce our Schottky detector that is currently used at least from almost 50 years. It's the same detector fabricated from Hewlett-Packard, Internet Technologies, and the Keysight, and now by VDI. And it's one that can cover from few megahertz up to 180 gigahertz. Of course, it's extremely expensive that we don't use it if we don't need it. It's around $100 each. And usually we need 8 or more, and always we lost them in each prototype. In the data sheet that it's still the same from the era or whatever. I don't know, even this one is HP or Agilent. It's the same SPICE model that was used from decades. And it's very close to the measurements we've done in the lab. That's why for the initial simulation, this is good enough. And it's very easy to implement. Of course, the diode can be used alone, but in the last years, maybe 10 years, we developed a kind of detector that is extremely performant and broadband. It was the first on the publication and now on the market. The problem with all the detectors in interferometry, especially in interferometry, is that they are not matched. That's why we put two different detectors like opposite, and with the help of the coupler, we reduce the errors in the matching here over a broadband. Of course, the problem is that we need more space and 2 diodes instead of 1, but it's a very, very good broadband detector. And here it's that detector that is implemented in ATS, and like in an easier mode that I keep it here. And measuring, we have more or less the same results as in theory. It means our detector works well, and you will see on the test benches that it's almost perfect. The same the gamma vector, and I put that here the red point. Always people claims whatever this kind of mixers are not good because of the DC offset, etc., etc. But as you can see, the center of the circle is so close to the center of the IQ plane that we don't really think that it doesn't work. And you will see in the theory that the DC component is less cancelled because of that differential action. The kind of history, I started with this kind of interferometric receiver. First was built almost 20 years ago here in INRS. You see all in that time, all it was in a waveguide, and people claim that it's not possible to integrate in a MHMIC technology because especially of the size of the number over 4, that's very very close to the thickness of the side frame. In that time, 10 microns. And it was really impossible to build on 10 mil substrate. It needs 254 microns. And we took that risk and we built our first circuit in 2009, 2012. And now we were the first in the world to build this kind of circuits, and now not too many companies. One single company we collaborate with, and one university in Germany. This evolution is like a kind of circuit. This interferometer is around 2 kilograms copper, and you see all the other circuits are external, connected with conventional waveguides that's still used today in all the equipment. And we reduce the size of the circuit more or less less than 2 by 2 centimeters, can be even smaller, but the problem is that we cannot work with our big hands. You see, we need to connect conventional waveguides here, and also SMA connectors, and we'll see how this one is connected on the test bench. That's why if this circuit will be implemented in the handheld receiver, will be really reduced in size. I will skip that theory, just I will show that supposing that we have this interferometer, and supposing that it's working well, we obtain two equations for the odd and the even outputs after the detectors. And each one has a very, very big, if you want, DC offset. That's why scaring all the, electronic engineers and the micro engineers. But after we have a small component of IF, we call it IF component, that can be even several gigahertz, where we can see the difference in between frequencies and also in the time, and also it's a phase shift. We can measure, and as you can see, Doppler and all in the ring. Finally, we built, like 100 years ago, a kind of circuits that are high impedance because the current is extremely, extremely low. We speak about nanoamperes, and usually with operational amplifiers that you can buy, we don't have anything. That's why we built a kind of circuit having a very high impedance, and the relation in between impedance and bandwidth, if the impedance is higher, the bandwidth is reduced, but we keep it more or less an impedance around 4 kilo ohm to have a bandwidth of several gigahertz. And finally, if you look in the theory, we have so beautiful two quadrature signals that where we have quadrature signals and also difference in between frequencies and between phase. And finally, that vector that is exactly like that one we use in the theory. Oh, it's too much theory. Okay, with that measurements, first we build a kind of simulation in ATS to be sure that our system will work with that circuit that we designed before. In the left side, we have the transmitter, the right side, the receiver, here the line of sight link. You will see in the photos on the right. This is the differential amplifier that we use. You will have all the presentation and the waveforms. And for example, for a QPSK, and with the same color that we will have on the oscilloscope, we can see that we can recover the signal that are transmitted in the baseband on the all four channels, and that the signals, the odd signals are phase opposite, the even signals are phase opposite, and if we make the difference, you see that this big voltage offset 2.6 millivolt will disappear. You see in the next slide, we are very close to 0.005. The same, including Schottky diodes. I will pass shortly. You can see that the Schottky diodes and the reflection there give some additional, if you want, noise here, but we still have the good receiver. And now I start to show you the prototypes and how that one works. If you recognize here inside, we have the interferometer in the center and 4 detectors, always using grounded couplers. Inside, in fact, we have 8 couplers and 8 diodes and additional transitions to the waveguide to the transmission line inside. You see the size is impressive, but the circuit itself is small because we need to put conventional wave and also to have enough space for the SMA connectors and the cables to reach the baseband signals for the oscilloscope. This is our test bench that is still in use, where we can replace transmitters, receivers, lenses to amplify the signal. Just to give you a short, some figures. The attenuation is 60 gigahertz, it's around 70 dB in one single meter. 70 dB, it means 10 million times in power. We don't have almost nothing in 1 meter. That's why we need to exploit the weakest signals that we can have and to amplify how we can. For example, we can use different antennas, lenses, you will see arrays, planar lenses. Here are different projects for my different students. One build the transmitter, another one build several receiver, another one build multiplier, another student is metamaterial antenna in collaboration with Professor Denini. And you can see the signals on the scope, and I will go more or less fast. But the most important that using around a few picowatts of power, we can reach 1 meter. Of course, if we use more power, in Canada it's up to 10 milliwatts, we can reach several few meters. But the problem is that generating even 10 milliwatts of power requires around 20 watts of DC power. It means it's not really great. It's less than 1 over, usually 1 over 1,000 or 1 over 2,000, 10,000 efficiency generating millimeter wave. They are wasting in centimeters. Of course, we can transmit gigabits per second, but we must take in account if we really need that gigabit per second data rate in whatever application, especially in the phone. I'm not a big fan. You see I keep the same color, and you see in the 8-point constellation, each point carrying 3 bits. We have where the energy is displayed. All the green are all the quasi, pseudo-random transition in between. And the big problem, one of the big problems, one is generating millimeter waves. The second one is aligning the antennas. You need more or less 1 or 2 degrees for alignment. The second one is the stability of the local oscillator. That one cannot be stable even if we use cable to synchronize. You see that more or less, if you want rotation here around the circle, is not a white noise, it's a kind of phase noise. And that phase noise, for the moment, it's difficult to cancel. Just now, the manufacturers start to change the reference from 10 megahertz to 100 megahertz, but we really need that reference to gigahertz to synchronize all the PLL. If not, that phase noise will be always present, and if we have many points in constellation, we see that it's really a problem. And once again, if you look here to the baseline signal in the time domain, you can see that the odd signals are in opposition, the even one are in opposition, and we can obtain this kind of constellation without knowing what kind of constellation is transmitted. I remember that in all the software that we use, you need to know from the beginning the number of points, constellation, modulation type, data rate, and all, and to upload in the software, if not the software is lost. This kind of interferometric transceiver is able to detect at once the modulation scheme, and you see what kind of demodulation. If you change the modulation scheme in the transmitter, I'll go back a bit. I will find there are too many slides. Here, if you change the demodulation scheme, you have at once the demodulator signal, and also, of course, you can see the spectrum in others. This is a bit a zoom of the circuit. This one is not an integrated one. It's especially built for students to be able to play with circuit and keep it alive. This one is still alive at least 10 years now. The others can be broken in fraction of seconds. That's why I introduced here a manual attenuator and a phase shifter, just to show to people that we can reduce the power of the local oscillator up to minus 40 dBm. And usually in industry, they use 10 dBm. It means 100 times, whatever, 100,000 times less. And why we need it? Because in this case, we don't need huge power to generate local oscillator. Imagine that you need to use your cell phone in whatever millimeter wave, the millimeter receiver, and use standard receiver. You need for each single oscillator around 20 watts of power, and your battery will be finished in seconds. Only feeding that oscillator means the actual technology is not ready, even if people claim that it can work for militaries, for specific application. I'm a big fan of that one, but not for cell phones. Instead, they use our technology. Okay, and in this case, you can see we have an external conical antenna, external noise amplifier, our block with the interferometer, only interferometer with diodes, and external baseband circuits. If something's happened, I just replace one of them. I have double trigger. For the moment, all still up. Starting from simple modulation schemes, you can see here four faster bit. QPS key, and you can see signals 1, 2, 3, 4. Of course, the blue is not really blue. When I save the GPN is not the same, but you will see that it's really blue when you look to the screen. We increase the data rate. Here we have 25 megacycle by second. The problem is not the receiver. The problem is the transmitter, because the transmitter that we have now, it's able to transmit only 20 megahertz more or less in modulation. It means whatever we try to transmit more, we cannot. Even if the transmitter, the receiver is able to transmit. But this we solve it like in a few months, because we received the OER grant, Professor. You see, we have here 16 modulation at one, and the energy is like focused in the good points, and it's a slight rotation. It was in purpose because I used the manual phase shifter to show the student that if something's happened, the constellation will rotate. And I will show you what's happening with the Doppler. This is really crazy. We have 8 points and 50 megacycle by second. Once again, the problem is more or less the generator, not the receiver. The receiver can work up to 3 gigabits per second. And I want to show you what's happening with the Doppler. Even supposing that we move our hand or we move slowly with 2 centimeters by second, the Doppler is 4 hertz at this frequency. It means all the constellation will turn 4 times per second, and we need to catch it. And there are several techniques to do it. Here, it's shown more or less just a BPS scale. Why people still keep 6 gigahertz even in 5G? Because usually to synchronize, it's extremely easy today. You send the BPS scale signal, it means you have only 180-degree in between signals. You multiply by 2 this one, it means no modulation. You divide by 2, it means you have a synchronous carrier. Whatever speed you have, you are in the car or you walk. Unfortunately, in millimeter wave, you cannot, because there are no multipliers. Multipliers more or less. We reach 120 gigahertz or more, but no electronics to divide by 2. It means you need to synchronize by other means, and it's not easy. I even don't speak what's happening if we walk. It means the constellation turns 400 times. Or if we drive, supposing that we have enough energy and the antenna is still alive. Supposing this one it's a dream. And you can see that it's impossible to catch even a BPS cable. Imagine that you have a 256 point constellation of 1024 point other things. But here it's another test bed that we built on the big screen. It was for visitors. You can see points, dots. We can play, but basically we use the same receiver and different transmitter. That one was borrowed by Keysight company, and it's working like up to 1 gigabit per second, and we reach this data rate. and validate that our receiver was correct. And even if you see here in the very high data rate that the symbol still on the circle, and if you go to zoom, they are opposite in phase and the circuit works perfectly. In fact, cannot, it is true because it's a passive circuit. And if the detector is speed enough, we don't have anything to, to do to reach that speed. This is one of the many integrated receiver that we build. The problem is always integrated circuits that are included. The big problem is the heating of the circuit, and we lost several receivers before taking an account that we cannot pull the receiver, the integrated circuit. This one is less than around 0.5 square millimeters. And the power dissipation is around 400 milliwatt. You need a fan, a big fan to pull it. And it's not included in the cell phone. And finally, we changed our mind, but even in this prototype that was working few minutes before exploding, we can see that we put different antennas, very simple antennas, and our circuit and all the transition to the conventional connector that we have. In another one, we managed to put the integrated circuit to glue it on the metal, and we don't need any fan. And here we can put whatever antenna you want, because now you have two different pieces. And we have also a collaboration with Professor Tairdelini for building this antenna. And finally, the receiver is here. X-ball is a kind of interferometer. They are not always the same, but it's always the same idea. 4 couplers, 4 detectors, and they are connected to the external connectors to be able to measure it separately. Okay. Next step is radar sensor. And we built several ones, but I will show you two. A 60 gigahertz one and 77 gigahertz. Why we need it? Because sometimes we need a really good resolution. The range is not big, maybe, I don't know, 30 centimeters, because of very reduced power here, less than 1 milliwatt. And as we know, for the radar equation, the power is even more reduced, like because it's like we have the radar equation where the energy transmitted, reflected by the target and transmitted back. It's 1 over the distance exponent 4. With the received power, it's almost nothing. Very close to the noise floor that is usually minus 80 million. The only difference, we keep always more or less the same box. You see, we have the connectors that is like WL12 connector, and the connectors, we call it baseband, but can be up to a few gigahertz or the SMA connector. And here, the only difference in between, if you like the first side, is the size of the antennas and the size of the interferometer and the size of the detector. However, I will just show the 77 gigahertz one because they are very similar in performance. You see a closer view to that circuit. You can see that the power transmitted here, the maximum is 7 dBm that is generated once again with around 12 volts multiplied by 1 ampere, minimum 12 watts. Is transmitted with the transmitting antenna. We don't have any problem with the synchronization because a part of that power is like feeding the receiver. And the other side is the receiving antenna that is like receive the signals reflected by the target. And the output, we have the output signals, I and Q signal, differential ones. Once again, differential to avoid all the DC offset, at least in the big ones. Let's see some measurements. This is the test bench, and usually I use some tools like metronomes, tuning forks, oscillating plates, fans, just to measure mechanical properties by electronic means at a distance. Here, for example, we'll try and we measure successfully the audio frequency of a tuning fork using the radio. Like this, for example, we can hear if someone speaks in the front of the window, the other side, just pointing the radar, we can hear it while they speak at the other side of the window. Because of very, very small vibration, we can see. Here are like some results of my Q signals. What you see here, for example, is the tuning fork and the hand that is moving, and you see the big movement on the hand and the tuning fork on the top. Here, comparing to the theory, the mathematical whatever calculation of what's happening with the tuning fork, we can see more or less the same. Once again, is the tuning fork and the hand. And if in the steady state, you can really measure the INQ. You will see better results if you want in the lower frequency radar that has a bit more power. Okay. For the metronome, we use a metronome and we can put different oscillation values here on the metronome, and we can, the target is this one, and we can see on the oscilloscope the frequency of the oscillation, and we can measure it that one a few meters distance. In this case, no more than 20 centimeters, but in the lower frequency case, you see 24 gigahertz, and the circuits are still on the market since 1980s. If this are more or less the same circuits, electronic was developed in that time for satellite communication and for local to multiple distribution system of the television. And the industry is still in that level from MHMIC circuits. All that MHMIC circuits for millimeter wave or for quasi-terahertz are in the development and are extremely expensive. That's why one of my approaches is to collaborate with the company to build a kind of very, very low cost sensor. Finally, they build it somewhere in California, but I just give some specs, no more than that. And finally, they give me all back, and I put it in the box in my garage and whatever. I use this kind of sensor to play in the lab, and it's only a few $100 each, 1,000 or whatever, few thousand, and honestly cannot be destroyed. This is the specification. It's more or less an interferometric sensor, but with conventional mixer. Our dream is to build this kind of mixers, whatever radars, like previous one, but including amplifiers, because that one are always almost only tasked. And that's why the range is only 20 centimeters. Here we can reach with this toy 10 meters, 15 meters, and it's very, very useful as a test bench. For example, here you can see the respiration of a person that is like 2 meters away. And you can see heart beating, we can measure the pulse, we can all this kind of medical application, of course, metronome and all. I repeat the tuning fork experiments. The tuning fork oscillating from 100 hertz to 4 kilohertz, and we did just to read the frequency, oscillation frequency of the oscilloscope. This one, the tuning fork is not keeping in the hand, and that's why the signals are really good. See, you can see IQ signals, almost sinusoidal ones. For the metronome, the same. The metronome is very close to the heart beating, but the signal is really strong because it's a metal tongue. What we think to do with this one, like 2 years ago in collaboration with Professor Raisa, we think, okay, we have that very low cost radar sensor, why we don't try to put some communication? And I remember my old days when I started engineering in telecom. At that time, we used frequency shift keying to transmit numbers. Even today, if you look to a keypad of the phone, when you push a button into 60 watts, there are 2 tones that are going up. And with that 2 tones, you have a signal. Of course, the big problem with microwave is the synchronization. It means if you try to put this one on the car and to communicate, will be so expensive that nobody will buy. And okay, we try to avoid Doppler. It means in the demodulator, we let the oscillator that is in the whatever in the receiver. I will explain the test bench later. We let it run more or less freely, and we put the transmission in the transmitter away from the oscillator, and whatever drift or Doppler is happening, the transmitted signals stay still away, and we can demodulate. For example, here it's a static test bench where we try to see if we can, modify a bit the radar to be able to be in the same time the radar and the receiver. And we put a pseudo-random transmitter, whatever, this is source, frequency meters, the transmitter, the receiver, and we keep it like 1 meter distance just for fun, to be easy to operate left and right. And we put also a spy, a kind of horn antenna, trying to see what's happening with the signals around. And we can see here, we have two signals, left and right, transmitted by the radar in the left side. And somehow, the local oscillator, the transmitted signal of the radar on the right side reflected somewhere in the room back. And we look to this one, okay, still looks like in theory, try to see what's happening. And we do some mods and some, small electronics inside the radar to modify a bit the circuit. I will not insist on that, but the problem is that we are able to recover in Y or in Q signal, the modulation signal. In case they are perfectly aligned, we have only one signal, but usually it doesn't happen because they are moving targets, moving objects. And whatever is happening, we still have a signal in one, in other, but usually in both. Because we cannot align to radars, to cars, to whatever, and all the reflections around. That's why if you look to the signal that we receive, okay, we always have signals in both. That's why we prefer quadrature radar. Of course, the signals here in whatever we call it blue, but we don't really blue. But in this one is the signals that are transmitted from the pseudo-random generator, and here the signals that are received. A small frequency drift. However, you can clearly see two different states of the voltage. Of course, we can increase putting 4 or even more frequencies. But for the communication we need for emergency communication in between, for example, in between cars, we are like on the road. We need to see, okay, the distance, the speed of the car in front of us or behind us. If something's happened, a big hole in front of us, just to transmit to the other car, just brake. And this can be automatic, And like this, we can save lives with a very cheap sensor. Once again, it costs like $200, no more than. And it's not a mass production, like just for friends. It costs a few dollars. Fine. And just to see what's a bit how it's working, like we put 2 of that one on chariots, and we try to move it. And you see the beauty of this is that whatever happens, you can see the Doppler, and from this Doppler, you can obtain the speed, for example. If it's an FMCW and we can FMCW, you can instantly see the distance. And on the top, it's our modulation. It means it's really a joint radar communication, because if you go in conferences, okay, they build a transceiver, or 2 transceivers, they transmit to joint 2 of them, they save the data. They are big machines, costly ones. This is really something that doesn't cost penny. And this is my student, Lima, showing the zoom. And even here, you can see that the bits are really the same. And the bit error rate measured was for 0. Cannot detect any error in 100 million bits, we said. And finally, I will finish my presentation with kind of interferometric mixers. Having all this experience in building interferometric equipment and radars, we had a project with Focus Microwave to build a kind of mixer, but they require 2 things. A band that is like, if possible, 40 gigahertz, a very low power consumption, and very small size to replace all the big boxes that you see on the vector network analyzer millimeter. For example, here it's another circuit that we built by students. It's a multiplier, integrated multiplier, and you see always I put the power consumption. Just to remember my student that millimeter waves are not green. 400 milliwatts. In a small chip that is less than 1 square millimeter that will explode if it's not blowing from the machine. I will skip once again the theory, but the idea is that we can use a half of the interferometer, and if we'll be able to design really wideband circuits, not that circuits like required in the V-band communication 57 to 64, or in a radar, for example, 71 to 76, 76 to 81, excuse me, or in imagery around 94. If we can cover at once 40 gigahertz, we'll be perfect. And we succeed, at least 30. Okay. This is like the kind of image of a very old circuit in the beginning, but the idea is that we build some kind of circuit. We have an interferometric, whatever high impedance amplifiers, and we work on the same way, the same diode. First we simulate, we go on the test bench where we put that box with the interferometer and around the signal generators. Usually that signals will be generated by the vector analyzer. And finally here, oscilloscope and the spectrum analyzer, just to see if the circuit is able to mix two different signals, whatever the frequency is in between 60 and 90, spaced by a few megahertz. If we can reach that intermediate frequency signals, that will feed the internal receiver of the vector network analyzer, and they will be able to use it. And to reduce the size of that blue boxes, usually even bigger one, to a few square centimeters. We need few square centimeters because of the flanges. The flanges will be always whatever, 12, 10, 8, 6, because in industry they always use kind of flanges because they are like, you cannot destroy. The connector is extremely expensive and fragile, but that flange can still function 10, 20 years. The life of such a This is a zoom, and if, as you can see here, it's a half of the interferometer. The same detectors. The only difference is that we work in very high impedance transmission lines, close to 90 ohm, the limit of the fabrication, and we cannot allow any error. Because once again, it's 1 micron, the width of the line is 1.1 mil, 25 microns. And if you scratch it or if you touch it, the circuit is just put in your hand. That's why all the circuits are in this kind of boxes, and I put a kind of window. Nobody can touch it side unless they try it hard. And you see the beauty of the demodulated signals. For example, a frequency of 90 gigahertz, when the powers are extremely low, once again in industry, they require 15 dBm or 10 dBm, and they use active amplifier, active multipliers, and power consumption is bigger. It's not a big deal here in this frequency or for the measurement equipment, but one day we will need to build this one in portable devices, not just in static setups. And after the baseband circuit, the sinus is quite beautiful. We have 7, 8 megahertz, but we can reach up to several, I suppose 25 megahertz, very beautiful. We keep it like narrow band to avoid the noise. And here is an image of the spectrum analyzer where you can see that the second harmonic is 20 dB loss, that means 1/100 the power compared to the first harmonic. It means the sinus it's quite close to a pure signal. I finished, not in the time, but yes, 1 hour and a half. Future work, we'll try to build this kind of joint radar communication sensors and systems, if possible, low cost, and we're surveying the MHMIC circuits to see, and we already, you see, acquire some circuits and we tested, we see if the data sheet is more or less close to the specs and to the measurements, usually not. And trying to find a good circuit and cheap one, and if possible, to buy few of them, not hundreds, not thousands, to see how we can use modern circuits, MHMIC, in our systems. For the passive circuits, we know how to do it. And we try to reach higher frequencies, if possible, more than 100. We hope 180, why not 300? But the problem is not to write a paper. The problem is to find an application for those toys. Because, okay, you can have a test bench, you can measure something, you can publish. But finally, if the range is 1 to millimeters, 1 to centimeters, I don't even speak of terahertz communication. They are very good for very high data rate, very short distances, for example, in between chips on the computer. Okay, I agree. But don't even imagine that you have terahertz communication in between two persons moving around at a low cost. Because you will not be able to pay just to finish. You see, I'm installing all radios. And all the radios I installed were extremely expensive at that time. For example, 2 radios were equivalent to a big house with a garden in 1920s. 2 radios. Are you able to pay for your cell phone, say $300,000, and to keep it 6 months, like they did 100 years ago, with similar technologies? Only coils, only detectors, because they don't have even a very poor vacuum tube. No, of course, not integrated, no transistor, but the price was extremely excessive. But we cannot imagine today to pay more than a few bucks for 6 months, maybe. 1,000, 40,000 is too much for a cell. I'm not a big fan. We'll exchange whatever, the portion for a quarter of a cell phone. I don't see any plus. That's why the technology is not really in the point where we can afford such kind of toys. In the lab, we use very expensive equipment just to show that one day, if the technology will be there, we'll have some interesting application. I don't speak of military ones or whatever, because today we have transmission of few kilometers using big powers, lenses, whatever, antennas, but military, they don't care about that. I put some selected reference, just few of them, and we can find it using the digital identifier. Usually there are 3 papers here, just to see more details in technical part if you are interested. I'm open to questions.
Thank you.
Thank you. Thank you very much. Thank you very much, Professor Tatu, for this very insightful presentation. You have been working on highly advanced technologies. This is very interesting. If people in the online have question, I will ask please to raise the hand, and we will go by the order. And I don't know also, Tarek, if people have questions on site, but we can start online.
We all the time.
Okay.
Start online.
Yeah, start online first.
You can see the demos on the lab on the day.
So online, please raise your hand. If you don't know, you can. Okay, so Rida.
Yes.
Yeah, we can hear you.
Yes, that's
Thank you for this presentation. And I have a question. Are your transceiver and radar projects conducted in collaboration with industry partners, or are they independent research, academic research?
No. I collaborate, especially with one single company, because they are like building, if you want, equipment, and they can sell it. You see, because the problem here is the price. And if you try to build a kind of receiver or transmitter, I don't know who will pay the price for the company, for the components or for the device. But testing companies like Focus Micro here, they try to use and they use this technology. Oh, the battery is running low. The battery.
Okay.
Sorry. When the cost is not a problem, for example, for metal equipment costing $200,000 or more is not a problem to pay the development and all. And that's why we work in the collaboration with industry, and they use our technology to build this kind of mixers. You see the last part of the presentation. Of course, they are not up to date. They are patent pending, and it's just like 5 years ago some measurements. But yes, they are interested. But the price of the equipment is high. One day, maybe will be some applications for, if you want, for ordinary people. But once again, we need to solve the price of whatever integrated circuits in a mass production, carrier recovery for the modulation, generating power, and especially aligning the circuit and very short range. All will be one day possible, especially if, for example, we keep our laptop on the desk and we reach few gigabits by second to some router somewhere, very close. But once again, moving around, pointing the antennas is not a really good step.
Yeah, thank you very much, sir. Is there a question? Please raise your hand, or if you don't know how to raise your hand, you can talk directly.
We can share the presentation. I can send you the last version.
Okay, so Frankie, Dakam Wapi.
Yes.
Please, you can.
Thank you, sir, for the presentation. I would like to know, does the equipment function work in E-band, like 19 gigahertz?
90, yes. Yes.
Oh, okay.
Yes, we work on that band.
Okay, thank you.
Here on the last slides, the beautiful demodulated signal in 90 gigahertz. That's why I put 90 just because it's the more or less the end of the band, 60 to 90. To see that it's still working. 60 is not a problem.
And is 90 the maximum, or you also go higher?
We need a bit more, but you see, the diode itself, it's in theory working up to 110. And not all the diodes are the same. I see beautiful sinus if you want 96, 97 gigahertz. More than that, we don't even try for the moment.
Thank
We
you.
try with another diode. It's another diode on the market. It's VDI diode that is working in theory up to 180. I have some, but they are very difficult to mount because it's a flip chip. This one is easier to mount. Not easy, easier.
So there is a message from Alon Newton. He says, thanks a lot for the interesting presentation. So is there any other questions?
maybe from here.
We can, yeah.
Yes,
No, but how do you?
طيب, yes, طيب, yes.
Just have one question. Oh, yes, pleasure. From the local. First of all, thank you very much for the presentation, which gave more details, especially for the students and also for the people online, in general things, set up for types. Now I have one question, especially about your system radar. I think it's like 55. 55, yeah. Just I have a question. There are some people who work in 77 gig for car radars. That's right? Yes. Is it working very well? Yes, but the problem is that they're usually more mechanical with horn antennas. Yeah, but it's working. Of course. Yeah. Like you see, our big radar is not a problem. It's only the cost of hardware. Because it seems I had one student at my group recently. Yes. In Amgen, with yes. They work in this band to develop some radar. Yes. The problem is generating. Radar is the simplest way to use the millimeter wave because you don't need to synchronize anything. Yes. See, it means you have a radar if you can generate the power and especially in the car, you have a big battery. You don't care about few watts. For the student, I think there is a future for millimeter wave. Yes, of course. I just mentioned another example from my previous student. I have one from China. He left now, he returned back to China. Now he's a professor, but he has his own company. Now he designed and fabricated millimeter wave radar. Yes, and he make a lot of money. Yes, of course. Just, it's a huge market. There is a hope there. Yes, it's hope, and it's a huge market. The problem is to make the cost of the radar low enough. For example, when I bought my car, my Volkswagen, they asked me for a simple GPS 5,000. Like mad. I will buy from $100 from somewhere. I don't need the GPS.
Buy the chip now. It costs $15.
I know, but it's the same.
With almost 1 gigabit.
If the price will drop,
they drop a lot.
A lot?
Yeah.
Okay. Well, put in the car.
TI now is between 15 and $50.
Yeah.
Bracket. Yeah, I agree with you. 20 years ago, it was very expensive.
My idea, I like to convey as message research. There is a huge future for millimeter wave. Yes. The point-to-point communication, high data rate, but not necessarily in the cell phone. No. No, but people think millimeter because it was like this. When the 5G was implemented, people we'll take, don't need any more microwaves, no more, we'll go in millimeter wave, terahertz, we have bandwidth and gigabit per second. No. People, they think now. No. More than millimeter wave, they work in terahertz. No. That's why there are specific markets, very focused, and you need to afford them. Yeah, it's just yes. The future is still there. No, it's not very positive. If not, I will not stay here 20 years. I will not stay here 20 years if I don't have any hope. But you see, you need to be careful when you speak about applications.
But Sergio, when we talk about small cells for cellular communications, I think we're working on 28 gigahertz, but I don't know, 60 gigahertz. Is this something feasible or no hope?
No. You know why? Because if you keep it, you need huge power, and for the moment, I don't know, I don't see any power generation. It means hundreds of milliwatts with a reasonable efficiency.
Initially, it will be 1 million.
Just I have one question about comment from Halim. Yes. There is someone here from, I think, States. This is the Rappaport. I know. He work and develop some setup at 28 and demonstrate that work at 28. But you know how they demonstrate. You know, I'm not criticizing anyone. And you can find they put 2 antennas, they put 2 big setups, and they put a vector analyzer on the other side. Okay. Because like this, with a vector analyzer, you can have the noise floor in the 100, whatever, 120, but the noise floor usually is -80 or even more if you go with data rates. If you want just to show a carrier, no problem. But in my opinion, if you don't go fast, you don't need millimeter.
Yeah, but still a future.
Still, yes.
Because
I know, even all the papers of Rappaport.
the idea for microwave is saturated in
Yes.
terms of technology and also in terms of research.
I know.
Yeah, people they should work in.
I know, that's why I'm here and I'm trying to work in research. But just be aware, not all birds can be eaten. We speak in Romanian. Some not.
We will eat it.
Yes, please ask.
About the expense that you have on a design, which, correct me if I'm wrong, comes the majority of the expense that you have comes from the substrate that you use. Correct me if I'm wrong.
Yes,
So, like, basically, what you're saying is that currently the cost is too high to have any implication on the industrial point of view. But if you can find like a solution to like lower the costs through take like substrate, maybe like less performance.
you see, there are some problems. The first problem is the range. Maybe, I'm not living in the town or in the city or in the house where each 5 meters you have antennas. So crazy. Even if I'm like a passionate amateur radar, I don't like it. But it means the range is short if you don't put too much power. Generating power inside the mobile device, I'm not sure. This is the main problem. And also, we don't use omnidirectional antennas in such kind of devices because we need to have a certain gain. It means maybe a few degrees. Okay, we can build the intelligent antenna, all this or that, but maybe for the, not for the terminal, handheld terminal. For a router somewhere, okay, I agree. You see? It means your application must be focused. Don't imagine that the millimeter wave or even worse terahertz will replace under 6 gigahertz frequency. You see? Because you see, when the 5G started, in the conference, even Professor Rapato, I was like you in the conference. Professor just started to tell us 2009 in the conference in the United States that in few years, 5G, forget it about all microwave, 4 gig, whatever, we'll have thousands of receivers, on our cell phone, with thousands of receivers and thousands of antennas, I don't even imagine how, we're able to cancel all and we have enough power and we have 1 gigabit per second each for the time of the Olympic Games in Tokyo. Did you see something? No. You will never see even for 6G, 7G, 8G, whatever it is. No, because you need too many antennas and space it on each 2-3 meters, and we'll be all dead, I suppose.
Okay.
Because of that energy. See?
Having protest, you need
You protest, I don't know.
He's young.
We speak, the conference is finished, we speak. But this is my honest opinion, millimeter wave have a big future. But on very specific application. Don't even think about that you can send your energy from your battery to our neighbor. So your neighbor having an account that first you will lose 1/1,000,000, you will have just 1/1,000,000 of the energy discharging my battery to fill the battery of the neighbor. All these are like good for publications.
Okay. So
visit a millimeter wave lab to touch. That's why I put voltmeters, ampere meters, whatever you want. You can see the power generated, the power that you use, and the power we have like consumption. And again, if you see 1/1000, and it's even more, then no.
okay, so I will thank all the attendees, and we thank again Professor Tatu for this very invaluable presentation. Thank Tarek and thank everyone for co-organizing.